So, all right, so I think we're at lecture 24. So welcome. Sorry. Yeah, great. So, all right, so let's crack into it. So, remember last time we talked about these deformations of boundary conditions, and we showed that well, what did we show? We showed that if we have this deformation of the boundary condition, then this induces a deformation of the operator. Okay? So let's start today with a corollary to all of this. The corollary is, so let P plus be a boundary decomposing projector for an elliptically regular boundary condition B, write B equals, so we know that we can do this, right? We know that we have some graph, and we can write it as the restriction of this graph to h half plus w plus. So we know this from this theorem, this graphical decomposition theorem. Define, so now we define a particular phi s. So phi s that maps us from, say, the B naught. So I'm going to write B naught as equal to V minus plus W plus. So this is the definition. So remember we have this, well, maybe I'll write the remark in a second. So now I want to map it to some boundary condition BS, which is equal to the graph of SG H half restricted plus W plus. And what is this map? So I'm going to define this map as V plus W plus equal to V plus SGV plus. It's a half, yes. Right. So where we recall that V minus plus W minus is equal to 1 minus P plus, right? Or P minus L2 over the boundary, right? So recall that we have this decomposition, and this is what, in fact, I'll write plus minus is plus minus, right? So that's the decomposition that's guaranteed by this graphical decomposition. So we have now a graph that takes us from the V minus to the W plus, and that's how we can write this boundary condition B. So we can see that that B at 1 is precisely this boundary condition, and B at 0 is the thing that we want to deform it to, right? So okay, so then phi dot is continuous from the unit interval into bounded into this bounded space B naught to BS. It's an isomorphism for each S in the interval, and the index of dB naught is equal to the index of dBs, which is equal to the index of dB. Okay, so this is really why we want to actually talk about these deformations of boundary conditions, right? Because the nice thing is that the index, if you deform an operator continuously, the index remains fixed. So this is an invariant, and we want to exploit that, right? We want to maybe start with very complicated boundary conditions for which we can, for which we have an index, and then we want to deform those boundary conditions to the well-known ones, so we can more easily work with a different boundary condition but an operator with the same index. Okay, so what's the proof? So from the construction, it's immediate, so it is immediate, yeah. No, it's a map. For each S, I'm defining a map. I mean, I don't understand the question. What do you mean? So the index is, this is a boundary condition now. B subscript S is a boundary condition. D is now equipped with the boundary condition BS precisely given by this graph. Yeah, so, yeah. This is a small s, yes, there's only one s here. Yes. Oh, sorry, I see. You mean, aha, you're right, yeah, so it's S maps. Yeah, so I guess it's B dot. Yeah, it's a bit, okay, yeah, you're right. That's, so actually that's a reason we shouldn't use this notation. I should say S maps to phi S, which takes me from, which is, from B naught to BS, continuous in S, right? That's really what I mean. Yes, you're right. Aha, okay. All right, so this is, so it is immediate from construction. I mean, so it's clear that it's continuous and it's an isomorphism. That S maps to phi S is continuous in the stated topology, and it is an iso for each S. Okay. Also, phi of 0 is the identity as we want. Let phi of S from DOM dB naught to DOM dBs, the induced isomorphism. From the proposition. So then we have that since the index is fixed, so then regarding, so let's regard, then we regard D, okay, so which direction does it go in? Let me see. Yes, D. So then we regard DBS composed with phi of S. This is now a bounded operator from dB naught. So the main point of doing this is that we have a fixed space now, right? So this is a bounded operator. So this is a bounded operator in this fixed space. L2ME is bounded. So in terms of the DOM dB naught, right? So I'm not saying that it's bounded in L2. I mean with respect to the graph norm. And therefore, the index of dBs composed with phi of S is equal to the index of dB naught. Okay, so that's from the fact that since the index of a continuous family remains fixed. Okay, but why? So now the point is that the index of this dbs composed with phi s is the index of dbs, right? But since phi of s is an iso, the dimensions of the kernel and co-kernel remain unchanged. So therefore, index of dbs is equal to the index of dbs composed with phi of s. Okay, so that's the proof. So the first thing is we want to adjust it so we get a continuous family from the same domain. So we can regard it as a bounded operator, and then we are able to go beyond this changing domains by noticing that the map that allows us to change domains is an iso, and then that means that the kernel, the dimensions of the kernels and the co-kernels are unaltered. Okay, good. So that's the proof of that. So now the point is that we looked at this boundary condition now that has this extra piece W plus. And what we would really like to do is to peel that away, okay? Because you see we have a W plus, and the amount that we miss in being able to talk about the full boundary condition P minus is the absence of this V minus part in this boundary condition B. But for that, we need a lemma. Okay, so let's now we want to relate the index of a dB to index, so to the index, to index of, say, dp minus h a half in the case of a bisectorial invertible. This p minus h a half is equal to the APS boundary condition with respect to A, right? So this is why we really want to do this. We want to know if we're given a spectral projection and we have the APS boundary condition with respect to that. Of course, as long as it's bisectorial invertible, we can always pass to that though. We want to know that we can perturb our elliptic boundary condition now. We want to deform it to the APS condition, but we're going to have some error terms. So we need to compute those error terms. So for that, we need this first lemma. For that, we first prove the following. So lemma. It's an abstract lemma. So X is a subspace of Y, is a subspace of Z, closed, well, okay, H, say, closed subspaces of a Hilbert space H. Then H mod out X is isomorphic to Y mod out X plus H mod out Y. Okay, so how do we prove this? So since H is a Hilbert space, we find complementary subspaces. taking the orthogonal complement, such that y is equal to x plus some x prime and h equals some y plus y prime. Okay? So therefore, h mod out x is going to be isomorphic to what? This is going to be y plus y prime mod out x. But now we expand the y plus the y prime in terms of the decomposition that we have. So this is now isomorphic to x plus x prime plus y prime mod out x. So that's good. So the x's cancel now. So we get that this is going to be x prime plus y prime. But by construction, what are these, right? So x prime is now isomorphic to y mod out x, and y prime is isomorphic to h mod out y, right? So which is now going to be y mod out x plus h mod out y. Okay, so very simple lemma. You can probably do that with your eyes closed. Okay, now let's, we don't need to talk about this at the level of boundary conditions that are elliptic, because the fact is more general than that. So recall that a boundary condition B is Fredholm if dB is Fredholm. Okay, so now the proposition. Let B1 subspace B2 be Fredholm boundary conditions. Then the dimension of B2 mod out B1 is finite, and the index of dB2 is the index of dB1 plus the dim B2 mod out B1. Okay, so very nice relationship. So the proof that I'm giving here is quite different. You can also find this in the paper of Beer-Baumann, or it's also, I think, using again so in the Beer-Baumann paper, it's using the equivalence of certain kinds of maps and their indices on certain kernels of surjections to the problem at hand, and of course that requires a more technical auxiliary lemma. And in the paper of mine with Magnus Gofeng and Hemant Sarachandran, we proved this using Fredholm, this concept of Fredholm pairs. But I felt that both of these proofs were somehow not suited to a lecture course, so this is an alternative proof which I think is simpler. So maybe this should really be included, in our paper also, because it's I think it's quite conceptual. So B1 is a subspace of B2. So what does that mean? That tells us that the domain of dB1 is a subspace of the domain of dB2. And also the range of dB1 is a subspace of range dB2 and closed, right? Since BI are Fredholm. Okay, so we can also we have that the kernel of dB1 is contained in the kernel of dB2. Okay, so these are all Hilbert spaces, right? So we can compute all of this with respect to the domain db2. So the main thing here is that, so we don't know whether, I mean, if we have a non-compact manifold, we cannot assert that the range of the maximal operator is closed. But what we have here is we have one operator that is contained that contains another, and we know that the range of this one operator is closed. We also know this is closed. We have a closed space here, a closed space here, and these are all closed spaces, right? With respect to, of course, the graph norm. Here, actually, the range is also closed with respect to L2. But in this instance, we're talking about the graph norm. Okay, so these are all Hilbert spaces. And so, what can we do? We can write the kernel of db2 is equal to the kernel db1 plus, say, a complement, right? The orthogonal complement, say. And now, of course, the kernel is a closed subspace both in L2 and in the graph norm of the domains. So I'm going to split the domains also in this way. And I'm going to write the domains of dbi equal to the kernel of dbi plus some remainder terms ri. Okay? Note, so what's the interesting thing about this, right? So note that the Ri is isomorphic to the range of the operator dbi. Okay, and what is the isomorphism? Via the map D that takes me from Ri to the range. Okay, so the point is that from the domain of the dbi to the range, it's a surjection. And the thing that gets in the way of it being an injection is, of course, the kernel. So if we have a subspace now complementary and away from the kernel, then we have that the map D has to map that to one-to-one to the range. Okay. Right. So okay, so also R1 is going to be contained in R2. Okay, because the kernel of db1 is contained in the kernel of db2. So if I take the, say, orthogonal complement of db1, so of course I should maybe write these are orthogonal complements. Let's take the orthogonal complement so we are fixed with these spaces. So we can certainly assert then that if I have db1 and I compute its orthogonal complement, then it's going to certainly contain hang on, is this the right way around? Yes, so okay, so what do I want to say here? Let's see, the kernel of db is, yes? Of course, that's by definition what it means for an operator to be, I mean, yes, so if you, I mean, for the only thing that changes is the domain of the operator, right? So okay, anyway, so all right, so where were we? So also we have that R1 is, so the domains are contained in each other. The kernel is of course contained, but the kernel of the db1 is larger, but we know that the range of the db1 is contained in the range of the db2. Okay, so that's the main point. Because the domain is smaller, the range has to also be contained in this way. And that's really why we have R1 subspace of R2 because we can write this as D inverse of these ranges. Okay, so now let's write dom db2 is equal to the kernel of db2 plus R2. And what's this going to be? This is going to be the kernel, I should say, okay, maybe I'll say since range of db1 is contained in the range of db2. Okay, sorry. And then, okay, so the kernel now of, so this is going to be the kernel of db1 via this splitting plus k plus, now I'm going to split, sorry, I should have written here, and write R2 equals to R1 plus R. So now we write this as R2 plus R. Good. Sorry, R1 plus R. And so then, sorry, yeah, look, it really doesn't matter which complement we use here. It just needs to be contained. Just needs to be consistent, done consistently. This can all be orthogonal complements, sure. But yeah, okay. So now the point is, so what do we have here? We can take the kernel of db1 plus the R1, and then we get the domain of db1 plus k plus R, right? That's what we get. So now we can mod out by db1. So we get that b2 mod out b1 is going to be now isomorphic to dom db1 mod out dom db2 mod out dom db1, which is going to be isomorphic to k plus R. Okay? So the point is that the kernels were finite dimensional, right? So the kernels of the operators were finite dimensional, and also the co-kernels, right? So, so in particular, okay, I'll get to that in a second. All right, so let's just leave it for the moment. Necessarily, K is finite dimensional since kernel db2 is finite dimensional by Fredholmness. Good. Now what is the co-kernel, right? So co-kernel db1 is going to be equal to L2 of the range of db1. But by invoking the previous lemma, well, I should write this L2 ME mod out kernel range db1. All right, so and then by the previous lemma we have that this is now isomorphic to L to mod out the range of db2 plus the range of db2 mod out the range of db1. And what is that? So the range of db2 mod out db1 is precisely R. Okay, it's going to be isomorphic to R because R1 is isomorphic to range of db1 and R2 is isomorphic to the range of db2. So this is now going to be, so what is this now? This is the co-kernel of db2 plus the, R2 mod out R1, which is precisely isomorphic to co-kernel db2 plus R, where I should say the second ISO uses lemma with, well, the right identifications, okay? So from this, So therefore, R is finite dimensional also. Okay, because the co-kernel of dB1 is finite dimensional and the co-kernel of dB2 is finite dimensional. All right. Okay. So now, what do we have? So what we've proven is that B2 mod out B1 is precisely K plus R. So let's now compute the index. So the index of dB2 is equal to the dimension of the kernel of dB2 minus the dimension of the co-kernel of dB2. So that's now, by this equation here, the kernel equation, well, it's just this equation here. This is going to be precisely the dimension of the kernel of dB1 plus the dimension of K. And now we have the co-kernel, so the co-kernel goes the other way, right? So it's a minus sign, so the co-kernel of dB1 is the co-kernel of dB2 plus this term R. So if we subtract away now, so we get minus co-kernel of dB1 plus the co-kernel of plus R, right? So so this is going to be minus dim co-kernel dB1 plus dim R. Okay, so now what do we have here? So now we combine this and we get the index. So we get the index of dB1 plus the dimension of K plus R. And what is the dimension of K plus R? Well, it's isomorphic to B2 mod out B1, right? So this is precisely now the stated formula. Index of dB1 plus the dimension of B2 mod out B1. Okay. No, we get this out of the wash, right? Because so what is B2 mod out B1? It's K plus R. So the first term, K, is necessarily finite dimensional because we have the kernel of dB2 and the kernel of dB1 are finite dimensional from the Fredholmness of the boundary conditions, right? So that means that K has to, because we're writing dB2 as the kernel of dB1 plus the K, then it means that the K has to be also finite dimensional. For the finite dimensionality of the R, it's the co-kernel, right? So it's from this calculation that we get that R is finite dimensional. So now we have the sum of two finite dimensional spaces, and that means that B2 mod out B1 necessarily has to be finite dimensional. Yeah. No worries. Okay. So so that's interesting that if you have two Fredholm boundary conditions, then necessarily, and one is contained in the other, necessarily the difference has to be finite dimensional. And there's no regularity assumptions here or anything. We don't need to use any elliptic regularity or anything like that here in order to make this work. It's just precisely and very elegantly just coming from the fact that we have the kernels and the co-kernels of the operators being finite dimensional. Of course, we have to use closeness here, right? So where we use closeness of the range of the operator, we cannot just use the finite dimensionality. We really have to use the full thrust of the Fredholmness an assumption for the operators, because we're taking the range of dB2 mod out the range of dB1. So if, say, the range of dB1 was not closed, you know, I mean, this is then dubious how we take these ranges and so on and so forth. So closeness is of vital importance also for the range. Okay, so now the theorem. Let P plus be a boundary decomposing projector and be elliptically regular. Okay. And write B equals to graph G restricted to H half plus W plus yeah, right, via L2 graphical decomposition with respect to P plus. Okay, assume further that D and D star, D dagger are coercive at infinity. Okay, so we need them to have an index with respect to the elliptic boundary condition, elliptic irregular boundary condition. Then letting, so I'm going to write B minus equal to P minus acting on H half of the boundary. Okay, so this is somehow like the generalized, what would be a generalized APS condition, in the sense that, I mean, we're just looking at the negative part of the boundary decomposing projector. If P plus was coming from a spectral projector, this would have indeed be a this would indeed be a APS boundary condition. Okay. We have that the index of dB, which is a general boundary condition, now we can write it really in terms of the index of this B minus plus the dimension of the W plus, so that's the amount of error here, but minus the dimension of the W minus, right? Where we have that B minus is equal to V minus plus W minus. Okay, so this is really using the structure of the decomposition. Okay. So how do we first prove this? So let B naught equals to B let B naught equal to V minus plus W plus. Okay, as in the previous proposition. Okay, so if we do that, we know from that proposition, we know that the index of dB is equal to the index of dB naught. Okay. All right. So okay. So now let me consider let us consider B minus plus W plus. Okay, we can do that. All we've done, remember that W plus is a finite dimensional subspace of H half. Okay, that's that. So which we know which is a, so it's finite dimensional. So adding this finite dimensional part to B naught still keeps it closed because the B minus is purely contained in the P minus, right? So this is let us consider this, which is an elliptically regular boundary condition, since W plus is in H half and finite dimensional, and B minus is, well, it's equal to P minus H half, right? So we're really adding on a finite dimensional piece from a complementary subspace, and so that's all kosher. Okay, so now what do we have? So we have that B minus plus W plus. So this certainly contains B naught, okay? And B minus W plus mod out the B naught is equal to V minus plus W minus plus W plus mod out V minus W plus, which is going to be isomorphic now to this W minus piece. Okay, so now we have two, so here we have two boundary conditions, each of which are Fredholm, right, containing each other. So now we can invoke the previous proposition, right? So by previous proposition, what we get is that the index of dB minus plus W plus is equal to the index of dB naught plus dim W minus. Okay. But again, we have also we have that B minus is contained in B minus plus W plus. And each of these are also Fredholm, right? They're elliptically regular, so hence they're Fredholm. And therefore, the index of dB minus plus W plus is equal to the index of dB minus plus the dimension of W plus. So now we have two equalities, and so if we just rearrange these two things, so combining these equations, we get that the index of dB naught plus dim W minus is equal to the index of dB minus plus dim W plus, which is the required equation. Okay, so we invoke this last theorem twice to travel between these different boundary conditions. But the upshot is that we are now able to precisely understand, you know, you give me any general boundary condition that's elliptically regular, and as long as the operators that we're working with are coercive at infinity, so they have an index, we can understand the potentially very complicated boundary condition in terms of the index of such an operator, in terms of the index of this fixed boundary condition which we compute with respect to a boundary decomposing projector of our choice. Okay, so we might want to change this depending on the kind of choices we make, and the W plus and the W minus subspaces can also be very explicitly understood. Okay, this really relates to the way that the boundary condition intersects with the P plus. So maybe I'll make the remark, right? So remark, this allows us to understand the index of a general elliptically regular boundary condition via the P minus H half E of any boundary decomposing projector P plus of our choice. The spaces, we will see later, that the spaces W plus and W minus can be explicitly described as, from memory, W plus is the boundary condition intersecting with the P plus of H minus a half, right? The negative half piece on the boundary, and W minus is actually isomorphic to the adjoint boundary condition, well, I should say the annihilated boundary condition, which is related to the adjoint intersecting with P minus star H minus a half. Okay, which is also now related, if you want to choose some related, not the related, but the induced adapted operator on the boundary from this for the adjoint problem. One can understand the W minus precisely from that, right? So this is somehow an error term of the kernel, and this is some error term of the co-kernel. This is one way to understand it. Okay. All right. So where do we want to go now? So split. So the main point of this is that we want to somehow move towards relative index theory, which we will describe in a second, right? Splittings and relative index. Okay, so let's now describe a somewhat different geometric setup. So for our purposes here, let M actually be a connected manifold without boundary. And let N be a two-sided hypersurface in M, i.e., so two-sided means that trivial normal bundle. Okay, then we can cut M along N to obtain a manifold M prime, which we can maybe write as M subtract N union N1 disjoint union N2. So what is so this is really the boundary, right? So where N1 is equal to N, N2 is equal to minus N, i.e. with opposite orientation. And the boundary of this new manifold is exactly N1 disjoint union N2. So let's have a look at some pictures here. So let me take potentially a manifold here, and we head out. Let's just make sure that we emphasize that it can be non-compact. And maybe we have this neck region through here, right? So we have this neck region through here that looks like a neck, and this is our hypersurface. Okay, this is our hypersurface N, and this is our manifold M. And okay, so from this now we go to this new setup where we have the manifold here, which now has boundary. Yes. Yes. I mean, yes. It's. I mean, yes. I think if you wanted to include. Yes, but in that case, you do what you need to do in order to make it work. You know, of course, if it doesn't work, then there's no point in doing it, right? So I think I'm not sure. I'm not sure about the language surrounding hypersurfaces, but I would think that it's like the language surrounding manifolds. Maybe if you want a hypersurface to have boundary, you have to more or less explicitly say that it's a hypersurface with boundary or something, right? So of course, for us, yeah. So we just have to take it to not have boundary, certainly. Okay, and now the point is, well, I should have drawn this in yellow. Bugger. So, so this is now, so this is N1 and this is N2, say, and the orientation, so this has an orientation like this, and the normal vector of this is going to point the other way, right? So it really has to be a switch to orientation. Okay, and of course it doesn't have to cut up the manifold into two parts like this. The manifold might be still connected. It might not disconnect the manifold when we do this, right? So certainly we don't have an assumption that it needs to disconnect the manifold. So this is, maybe I'll just write, this is n, and this is equal to minus n. Okay. And this is, oops, this is m prime. Oops. Remark, m prime need not be disconnected. Okay, now so now let's have a look at some auxiliary data on there. So for a density mu and bundles EF on mu on M, I should say. On M and bundles on M. There are the natural objects mu prime, E prime, F prime via pullback to M prime. If we have a differential operator now between E and F, then we obtain a differential operator, well, order M in fact. Well, I'll keep it order 1 because we're talking about order 1. Then we obtain a D prime in diff EF prime, right? So all of these things are quite natural. Okay, so what do we want to do with this now? So the first thing is the lemma, the following lemma. Suppose that A naught is an adapted boundary operator on N1 equals N, okay? Then minus A naught is an adapted boundary operator on N2, and A equals A naught plus minus A naught is an adapted boundary operator on the boundary, right, which is the disjoint union of N1 and N2. So the proof of this, well, it's not hard, right? I mean, if we have a opposite orientation, then the adapted operator also has to change. Okay, so I'll just leave that as an exercise. Remember, an adapted operator is governed by first prescribing, is related to first fixing a transversal vector field along the boundary. So now if we have an opposite orientation, the vector field is going to be minus of the original one. And so the operator also has to change. I'll just make a quick remark though. L2 on the boundary is what? This is going to be L2 of N1. And of course, this is an orthogonal sum, right? It's an external sum, but it's an orthogonal sum of L2 on the boundary of the second copy. Okay, and by what we've said, so H check now of this D prime is going to be what? This is going to be, we can describe this as the H check A of the D. So if we apply this now via this lemma, what we get is precisely on the N1 part, right? So we get chi plus A naught H a half, chi minus A naught H a half, So we can always describe this in terms of the manifold N, right? Because N1 and N2 are copies, so it's useful to be able to maybe, okay, I'll write N1, N2 here, but really it's saying it's two copies. So this is just really two copies of N. Second M, okay. So now the check space, what happens? So the form of the adapted operator is A naught and minus A naught. So we have chi minus of this A naught H1 plus chi plus of, well, I'll put N1 here and N2 here as just for the moment, A naught H minus a half of N 2E. So this is for the first copy, right? So this is where the L1 corresponds to. So plus, now we have chi minus A naught H half N1 of E plus chi plus minus A naught H minus a half N, well, I'll put N of E here, right? I'm just going to drop, just like in the second thing, I'm going to drop these two. So what does that mean? So it means that the check space now looks like the normal check space that we're used to, where we have the negative, the half regularity on the negative projector with respect to the A naught. Oops, N of E, minus a half. And then in the second copy, we get actually chi plus A naught H half. If we want to describe it in terms of this A naught, chi minus A naught H minus a half N E. Okay, so that's the weird little thing that happens when we have this. So the negative spectral projection part is this. Okay, so this is really the negative spectral projector, and this is the positive spectral projector. Okay. So another thing I want to just point out before we move to the theorem that I want to prove today. So D deep dagger are complete and coercive at infinity if and only if D prime and D prime dagger are. Okay, so why is that true? Well, this follows from the definition using the fact that the N is compact. So I hope I said that N was compact. Maybe I didn't say that. Two-sided compact hypersurface. That's a more serious omission than having boundary, not saying it's compact. We have to really cut it along something compact. So this follows from the definition using the fact that N is compact, and I'll just leave it as an exercise. Okay. So now the splitting theorem. The last thing I want to do today. So this is due to Baumann in their paper. So I was hoping that, well, I'll remark on it in a second. So let M mu E F and M prime mu prime E prime F prime be as above, and D in diff 1EF elliptic with induced D prime in diff 1EF prime elliptic. Okay, suppose that D prime are coercive at infinity, and that D prime admits formally a self-adjoint invertible adapted, well, we don't need to say self-adjoint adapted operator on N. So let B1 subspace of so let B1 be elliptically regular. So B1, I want this to actually just be a subspace of N1, right? So this is in H half of NE be elliptically regular on N1, and B2, let's define this to be the L2 orthogonal complement, but sitting in H half of well, N of E. Okay, so the point is that B1 plus B2 now equals H half of N. Okay, considered as a boundary condition on N2. Okay. Then the index of the operator D, which we know has an index, right? Because D and the formal adjoint of D, we are assuming are coercive at infinity. So they certainly have an index because the manifold, the original manifold M is without boundary. So then this is equal to the index of D prime B1 plus B2. Okay, so the proof. So, so how did this happen? So before we get into the proof, unfortunately, I wanted to discuss something else, which I should really have included as a lemma. So, so before that, let's talk about the following, right? So it's a very important boundary condition called the matching boundary condition, right? So lemma, the boundary condition B equal to 5, U such that U in H a half on N E is called the matching condition. Well, maybe that's a definition, right? Okay. Lemma. So this is for the setup that we have, right? So lemma B is elliptically regular. Okay, so how do we see this? So actually this doesn't require, so the matching condition certainly doesn't require us to have a self-adjoint adapted operator, right? So the proof of this, so let A naught be an bisectorial adapted operator, and what do we write? So we write V minus equal to, so what should we write here? So this should be chi minus A naught H half NE plus chi plus A naught H half NE. Okay, because this is the negative condition now for the full object on the boundary. And then the V plus I'm going to write as chi plus A naught H, oops, sorry, it's got to be L2, right? These are L2s when we write the V spaces. L2 NE plus chi minus A naught. So, yeah, okay, what is really the right way to write this? Yeah, that's okay, it's okay. L2 NE. So now we have to give a graph, define G equal to just the map. So this has to go from V minus to V plus by G equal to ID, right? So this is with respect to L2 of N1 E plus L2 of N2 E going back into itself. So now what do we have? So now we claim, so let's look at the graph. So the W spaces are empty, right? So because we chose our adapted operator to have no kernel, the W minus is equal to 0 and then the W plus is equal to 0. So now let's look at this graph G. So the graph of G, so the graph of G is equal to what? So this is equal to U V plus G of UV. Okay. such that u v sit in h a half, well, such that u and v is in h half of ne. Good. So what is this? So this is going to be uv plus, so this just interchanges the slot, right? vu, such that uv is in h half on the boundary. And that's precisely equal to u plus v and u plus v, such that uv is in h half of the boundary. And this is precisely of the form that we want, right? So this is now equal to this, well, I should maybe let me call this boundary condition Bm for matching, right? So this is equal to the matching condition Bm, because it's of the form u plus v for uv in h half. Okay, and this, by the theorem, by theorem, we know, but we have that Bm is elliptically regular. Okay, and all right. So we still have time to finish off the proof. So the proof of the splitting theorem. So the proof of the splitting theorem is, so let Bm be this matching condition, right? So this is going to be uv in h half n1 e plus h half n2e, such that u is equal to v, right? So this is really what the matching condition is. The matching condition. So on identifying the pullback sections, say via a map phi from E to E prime, we get that the domain of dB is equal to the domain of D, right? So why is that? Well, because we've cut along this n, but now we are using matching conditions so we can go over this n, right? So this is precisely just as if there was no boundary. So moreover, the index of dB, there's an m here, dBm is equal to the index of D. Okay, so now the point is choose A naught invertible self-adjoint. Adapted boundary operator. So that's always possible because we've assumed that we have a self-adjoint adapted boundary operator. Therefore, we can always subtract some small epsilon and obtain that it's invertible. Okay, and so now let's compute with respect to that. Okay, so I want to decompose the boundary conditions. So I want to decompose the boundary conditions now with respect to this. So as we saw before, the V minus is equal to chi minus A naught. So this is equal to what? This is equal to V minus 1 plus V minus 2. And the V plus is equal to V plus 1 plus V plus 2, where V plus minus 1 is equal to chi plus minus A naught L2 M L2 NE N. And the V plus minus 2 is equal to this with the sign flipped, right? So this is going to be chi plus minus of the negative A naught of L2 NE, which becomes chi minus plus of A naught L2 NE. All right. So now if we write these boundary conditions in graphical form, this is going to be W plus 1 plus the graph of G from V minus 1 to V plus 1 intersect H half. And the B2 is going to be what? W plus 2 plus the graph, sorry, there's a G1 here, G2 going from V minus of 2 to V plus of 2 intersect H half and E. But since B1 is orthogonal to B2, and also B1 plus B2 is equal to H half, well, I shouldn't say that, in L2, right? I should say this is orthogonal in L2, and B1 plus B2 equals to H half and NE. We have that V plus minus 2 is equal to V minus plus of 1, and the V W plus minus of 2 is equal to W minus plus of 1. And the G2 is equal to G1 adjoint, negative G1 adjoint. Okay. So the adjoint boundary condition so this really uses the self-adjointness, right? So I should have really remarked that in the graphical decomposition, the splitting that we get is actually they're orthogonal splittings if we obtain that the underlying spectral projector is self-adjoint. So that's self-evident from the fact that these if A is self-adjoint, then these projections are also self-adjoint, right? So I should have maybe explicitly stated that. Okay, so now the adjoint boundary condition is what? It's precisely equal to, for B1 plus B2 is B2 plus B1. Right, so the W plus space here is what? The W plus space is going to be equal to W1 plus W1 minus, and the W minus space, by considering the adjoint boundary condition, is precisely equal to W1 minus plus W1 plus. Okay? Therefore, the dimension of W plus is equal to the dimension of the W minus yes, maybe the order switched, but they're the same. But the big W's here is the splitting of the large boundary condition B1 plus B2 with respect to what we have. Okay, so the dimensions are equal, and therefore by theorem, what do we have? We have that the index of D is equal to the index of D prime B APS with respect to this boundary condition A naught, and that's actually exactly the same as the matching boundary condition, right? So by the lemma, the APS boundary condition we saw is really the matching boundary condition. We can deform this boundary condition to the APS, right? Because I mean, here we've taken the graph, but if we deform this graph, we get the APS boundary condition. I should have maybe said that. So this is now equal to the index of well, okay, so maybe I did say this here because I introduced the matching. I only wrote the matching. So this is equal to D prime B M, and and this is equal to the index of D B1 plus B2 as we have just seen. And I should say where the second equality comes from the graphical from deformation of BM to BAPS A naught via graphical decomposition. Maybe I'll include that as a lemma in the next thing. Okay, that's all we have time for today. I'm not going to do any more. So the idea is that we want to now use this to prove the so-called relative index theorem, which arises in the study of positive scalar curvature metrics. Okay, so that's really the only application that I want to give of this, because that's a very important application. It's really a modern and active area of research. When I was thinking about, so this is really on the state of the art now. So when I was trying to prepare for this lecture, I actually tried to construct this proof and think about conditions on B1 and B2 that would allow us to prove this for the general case. So where it fails in the general case is it's really because we have that the B1 and the B2 are L2 orthogonal, that we're able to assert that these spaces are equal in this way. So if we didn't have that, we don't have a nice way of, so if we took the adjoint boundary condition when A naught is a general a bisectorial invertible operator, the adjoint operator then is going to map the A naught star. So there's a change of space, and so maybe this proof still works, but I think then it has to somehow, a lot more care needs to be taken to ensure that you won't get the quality of these W minus and the W plus spaces as we have, but what you would likely get is that the dimensions of these spaces are still equal. And so in the invocation of the theorem that we need in order to equate the index, I would anticipate that this goes through by a more clever construction. Okay, that's all I have to say for today. Any questions? No, because it's the operator on the boundary-less manifold. So we start with an operator D that is both that for which the formal adjoint and itself are coercive at infinity. and complete. Oh, I should have said complete. Sorry. Of course, we need completeness for all of this, right? But that should be in this lemma. Yeah. D and D prime are complete and coercive at infinity if and only if... D and D dagger are complete and coercive at infinity if and only if D prime and D prime dagger are, right? So I should really say coercive at infinity and complete. Sorry, that's an important note, because otherwise, of course, you could have weird things happening that makes it look as if there's a boundary, right, at infinity. Complete and coercive at infinity. Yes, that's true. And so the point is that the completeness says that nothing can go wrong. There's nothing like boundary that happens at infinity, and the coercive at infinity says that it has an index. And then the idea is that we can equate this index to giving, a boundary condition on one of the boundaries, which is elliptic, if you just pretended that you didn't have the other part of the manifold. But then the boundary condition that we need to take is the orthogonal complement that sits in H half. And that's also guaranteed to be a boundary condition because B1 is a boundary condition that's elliptically regular. So yeah. Any other questions? Aha. You should send me that so I can fix it. Yeah, thank you. Yeah. Okay, if there are no more questions, we'll call it a day, and yeah, see you next time.